All right, so we are recording. Happy Thursday, happy June 16th. On Monday, there will be no class in celebration of Juneteenth Day. So remember, no class on Monday. It is a university holiday. We're going to slide 78. Let me go to slide 78. So we're almost through chapter 8. We'll go on to the chapter 8 homework today. So last time we talked about this conversion to an epoxide. What this? Yeah, it works. So we have this epoxide right here that we're forming. We have a transition state. We get the epoxide, and they said we use the periaxide is used as a reagent. So there's all different types of reagents that can be used. I don't expect you to memorize all this. It's here. As long as you know how to use your tools. So conversion of alkene to an epoxide. First, we have this proton transfer. Then remember, this is the oxonium ion right here. We have a nucleophilic attack, and that's where this comes in right there. Proton transfer, this water is going to take a proton from the oxonium ion. It's going to deprotonate it, and we have this in an anti-addition, plus the enantiomer. Note the similarities between these three key intermediates. You have a protonated epoxide, a bromonium ion, and a mercurium ion. There's ring strain and a +1 formal charge. You can see this. It's all in a cyclopropanes. A 3-member ring, which there's a lot of strain on this. This is the most strain you can have. We talked about the cyclopropane and how that was the most strained. No, this is not a cyclopropane, but we still have a 3-membered ring, and we still have a lot of strain right there. So all three yield anti-products because the nucleophile must attack from the site opposite the leaving group. So you can do syn addition, same side addition. So it adds the alcohol groups. So both alcohol groups across the pi bond in a concerted syn fashion. So if you want both alcohol groups to be on the same side, you'll use this osmonium complex. But it says osmonium tetraoxide is expensive and toxic. NMO or an alkyl peroxide is used as a co-oxidant. So only a catalytic amount of osmonium tetraoxide is necessary. Seems like you can use this too, get the same results. Syn dehydroxylation can also be achieved with potassium permanganate, but only under mild conditions. It says cold temperatures. So under cold temperatures, we can get this right here. But it is limited because this compound, potassium permanganate, reacts with many other functional groups. Here we see the carbon-carbon double bond. Carbon-carbon double bonds are also reactive towards oxidative cleavage. Ozonolysis is one such process. So, you have here they're showing ozone right here. Ozone is in resonance with each other because this double bond can move. It moves right here. If that goes right there, those electrons are released. And it shows the reaction right here. So we have to use some type of mild reducing agent, DMS, dimethyl sulfide. Your dimethyl sulfide. So, what we form is some type of a ketone group. In this case, we form acetone, 2 equivalents of acetone. So electrons come in here. This double bond comes here. We have a 5-membered ring complex. Now there's some bond shifting, as you can see. This comes in here, and once we have this ozonide, we use a mild reducing agent to reduce it down to this. So it wants us to predict. We'll draw this. Right here. If we could look back right here, that ozone group is going to, break that open, and we're going to form some groups like this. They are ketone groups. Just count the oxygen or the carbons real quick. 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 carbons here. There's 9 carbons here. And they use the mild reducing agent right there, dimethyl sulfide. All right. To predict the bicyclic reactant used to form the product, and we did that right there. So, you want to analyze the reagents used to determine which groups will be added across the carbon-carbon double bond. Determine the regional selectivity, Markovnikov or anti-Markovnikov, and we did go over that earlier on in the chapter. Determine the stereospecificity, syn or anti-addition. And let's just see if we can, I just want to see quickly if we can find where it says the Markovnikov or anti-Markovnikov in this chapter. Says for the Markovnikov, it says recall there are 2 possible products. See. So for Markovnikov addition, we added that bromine group to the more substituted part, and the anti-Markovnikov addition was added to the, the less, the least amount of substitution. So it'll go on to the right side, and we controlled that with this peroxide. I just wanted to go back and show you the difference between Markovnikov and anti-Markovnikov addition. It says to plan a synthesis, assess the reactants of products to see what changes need to be made. You can see here we have a substitution versus elimination. Here's an addition reaction. It's you plan a synthesis, assess the reactants and products, give reagents and conditions for the following. It says addition reaction, add hydrogen and OH, Markovnikov regiochemistry. That's why you see this OH group, on the more substituted portion rather than right here because they want the Makarnikov regiochemistry. So we will put these reactants, water and sulfuric acid. All right, so we saw that. Changing the position of the halogen, the following transformation cannot be done with a single reaction. So first you'd have to have elimination. That means we're going to get rid of that bromine through either E1 or E2. Then you can do the addition. So to do the elimination reaction, the base needs to be carefully chosen. Remember the difference between the Zaitsev and the Hoffman product. The Zaitsev was the more substituted double the alkene, and the Hoffman product was the least substituted alkene. So we're going to use sodium. We're going to use this sodium O methyl group right here, where that where this group right here can easily take off, the hydrogen that we're interested in. That's the methoxide group. So we're going to use sodium methoxide versus the T-butyl group, the T-butoxide group. You may ask, why is there a sodium or why is there potassium? That's the counter ion right there. Otherwise, this would be negative, so you need to have a positive. So that's why you see sodium with the sodium one, and then you see the potassium with the T-butyl butoxide. So that methoxide group is going to take that proton, and now we got the Zaitsev products. And once we have that, we can add our bromine to it. It says, consider the following transformation. It says this is not a simple substitution, addition, or elimination. So two processes must be combined. First, we do an elimination, and then we do an addition of a hydrogen and a alcohol group. Here they're saying to use tosylchlorine and pyridine, and then here we're using our T-butoxide group. And we're going to get more practice with this stuff when we go to our homework questions. So the addition reaction must give an anti-Markovnikov. We talked about what that meant. Just changing the position of a pi bond. If you want to change it from this side to this side, again, they're saying two processes must be combined. You have an addition. We got that bromine, and then followed by elimination to give the Hoffman product. So we didn't want the Zaitsev product here. We wanted the Hoffman product if this is what we're looking for. The Zaitsev product would have put the double bond here. So it's just some terminology they're trying to get you used to. So for anti-Markovnikov, use HBr, use that peroxide. Elimination to give the Hoffman product, the T-butoxide, which is a bulky base. Think about that. If you have you're pulling off from here or from here. If you have, the methoxide, that methoxide is going to pull from right here. So you have to have that, this T-butyl group, and you're going to pull right here. It has more sterics going on. So if I draw that like that, there it is. So that T-butyl group has a lot of bulkiness. We're not going to be able to come in on this side. So this is going to be an X'd out. So we've gone over a lot of different items here: Markovnikov, anti-Markovnikov, acid catalyzed, hydroboration, hydrogenation, bromination, halohydrogen formation, and ozonolysis, anti-ensign, dehydroxylation. So there's a lot of stuff that went on in this chapter. Here's like an overall outline, of different reagents for making different products. We start with the same substrate, but we add different reagents to get the desired products. All right, so I don't expect all this memorization, but you could practice if you want to. So just refer back to the previous slide. So I'll just leave this up. Maybe you're copying this down right now. All right, so on your free time, go ahead and practice just inputting in what reagents you would use to put that in. And this may help you out on the homework. They go over some different mechanisms, and like I said at the yesterday, if you go to the back of chapter 8, it has a really good section for the mechanisms for this. So I highly recommend everyone go to the back of the chapter. And this is pretty much it. They're just going over some example mechanisms, and we're going to be going over some mechanisms in our homework. So why don't we go ahead and open the homework. So I'm going to go ahead and pause the video while I get that ready. All right, we're going to resume the recording. I have my chapter 8 homework pulled open. Hopefully you do too. If you're listening asynchronous, you can always pause the video. So why don't I go ahead and share my screen? Oh, it's wrong screen share. I want to share the chapter 8 homework. It's somehow sharing the wrong. I'm just gonna have to pull that down. Okay, so we're sharing the right screen now. So we'll go to question 1, like we always do. Pull up the pen. So indicate the general type of reaction represented in each of the reactions. We have a double bond, and then we're forming, we have Y and X. So that's going to be an example of an addition reaction, right? Here we have some type of X, and we're getting rid of that X. We're forming a double bond. That's going to be elimination. And here we have X, and we're changing with another variable, and they call it Y. So that's a substitution. So I'm just going to write sub. right, I don't see any questions. For question 2, it says classify the mechanism as a substitution, elimination, or addition reaction. They're showing you this carbanion, triple bonded carbon. It's a carbanion. It doesn't want to stay this way. You know, it wants to get rid of this formal charge. Chlorine doesn't mind to have a formal charge of -1. And I'm going to draw the chlorine on the opposite side. It'll make it easier to see. Let me see. It doesn't matter really. Let's get rid of that. That's what's going to happen right here. So we have a substitution reaction. Because we're substituting the chlorine with our alkyne. So let's go on to question 3. Question 3 says, you know, we have this going on. You know, they have this and there's a hydrogen, and then you're adding water to it. And then somehow we add that water to that double bond. That is going to be an example of an addition because we're adding that alcohol group to that double bond. For 4, now they want us to draw the mechanism. So we have this, we're going to have an addition, just like we talked about on question 3, but this can be with chloride. Here we have this HCl. HCl is a good strong acid. So it doesn't matter where we put this. This is going to happen. And then what we're going to get is we're going to have addition of that hydrogen. Now we're going to have, we can just draw that out a little further. A positive charge right there with the chlorine. So I'll let you look at that. So question 5, they want us to draw the product. We have, let me see. We have an addition reaction again. And we have this. It's going to come out here. This is going to leave. This will become positive. Then that chlorine is going to come back in. So that's what you're going to get. Any questions on that? That was question 4. Oh. What was that question 4? Oh, that was question 5. Question 6, they give us the end product. Okay, they give us the reagent HBr. They give us this right here. We got to kind of think of, we have to work backwards on this. So to do that, we still have this cyclohexyl group. Have this. Now we just have to determine where to put the double bond at. We'll put it right here. We put the double bond there, then this can take that proton, and that Br can come in right there. So that's why that makes sense to put this as our answer. All right, question 7. 7 has this. It has this compound. I'm not going to draw the hydrogens. I will draw the hydrogen for this one. HBr is a strong acid, so it's going to take that proton right here, and Br is going to release itself. The bromine group is going to release itself, and we are going to get something that looks like this. And wherever I didn't draw a hydrogen, there are hydrogens there. So we're leaving the formal charge on the secondary carbon. That makes sense, because the secondary carbon is more stable than a primary carbon. So any questions on 7? You guys are quiet on me, so I just want to make sure you're engaged. So now we're going to a little bit different. Remember we talked about, we have the Zaitsev product or the Hoffman product, and we can get, we can change where the direction of where the bromine is going to add based off of maybe what reagent we choose. So we have HBr, we've been doing that, but now we're going to add peroxide. So when we add that peroxide, we're not going to add the bromine right here. The bromine is actually going to be added right here, because this is going to go here. Now the hydrogen is going to come here. We'll have that formal charge here, and the bromine will add there. So it's opposite of what we've been talking about because we have that peroxide. So now we're going to have this bromine with that methyl group coming off right there. So hopefully that makes sense. And that's because we have that peroxide. We added something extra to it. All right, so that was question 8. We'll go on to question 9. We're moving along pretty good here. So once you get in to start doing the problems, they're not too bad. So we have HCl. So again, we'll come here, we'll take that. It's almost like playing chess or checkers. So we take that hydrogen, and we have this positive charge here. We have the chlorine. Do you think it's going to go here? Or do you think we're going to have a hydride shift? So we'll have the hydride shift, So once we do the hydride shift, we're going to erase that. We're going to put the positive charge here. Then we'll have the hydride shift, and this is going to get redirected here. So now you can see why we have the chlorine here. Because a tertiary, whenever you can form a tertiary carbocation, that is the most stable. And there are instances where that doesn't happen when you use that mercury compound. Then we're not going to get any arrangements. So it really all depends on what you want to do. So 10, we have a symmetrical molecule. If you want me to go back, I will. We have this symmetrical molecule that looks like this. If I'm not drawing the hydrogens, it's implied, that there'd be 3 hydrogens here. Now we have this, it's acid catalyzed in water. And remember, this alkene will not react with water without the presence of an acid catalyst. So it's really important to have that acid catalyst. This is a key step for this to happen. So with this, this will then take a hydrogen. And it doesn't matter where we put the positive charge because it's symmetrical. And then we have that OH group, and it can either go here or here. It depends where you put the formal charge. It's symmetrical, so it doesn't really matter. So So we get something like that. All right, so we'll go on to 11. It says use curved arrows to show the attack on the electrophile. Let me just look at this. So we have H3O plus. Okay. So we have this. And we have H3O plus out there. And it's going to take a proton. It's going to get released like that. Positive charge here. Go in. Act as a nucleophile. And we're on part C now. And another water is going to take the is going to deprotonate that. It's going to become a deprotonation there, and these electrons will add here. And that'll give us our final products. So we have part A, part B, and part C. Right, that was 11. We'll go on to question 12. We are moving along really good. Question 12, they just want you to draw the structure. So they say draw fumarate or trans-butane dioate. So we'll do that one. And then they want us to draw S-malate. So we'll go ahead and draw that one. So there's two drawings that you have to make. So we'll draw the hydrogen there for you so that you can see where that's at. So this is in the S position. And that was that. All right, so we are going to question 13. If you want me to slow down, just let me know. If it's a good pace, let me know as well. I don't hear anything. Question 13. Draw the structure of two alkenes that would yield one methyl cyclohexanol, but treated with, so we're going to treat it with the mercury compound, right? So they give us this alcohol group, and they want us to know what would the starting products be. Remember, sodium borohydrate is a reducing agent. So the starting products will be, we're going to have that cyclohexane ring. So we'll have two of them. The only difference is we'll have one here, and we'll have one here. So these are your two starting materials. You got something in the chat? All right, so someone said I'm doing at a good pace, so I appreciate the response. All right, so we're going to question 14. It's not clicking. There we go. So they say draw the major organic product for each of the hydroboration. Remember, B2H6 is a dimer, a boron. We have this. There's some type of dimer right here. Anyways, we have two reactions actually. So we have reaction A. We might have to use, we'll use two slides. What's the difference? We have all kinds of slides. It's not like a chalkboard. And we have to do something with that. So when we do that, we are going to add an alcohol here. And I guess we can put them on the same slide. And for this one, we're going to add the alcohol here. All right. right, so hopefully we have those down. All right, so let's go on to 15. 15, it gives us a couple compounds. It says be sure to draw hydrogens on then it once is so 15 is kind of involved, to be honest with you. So this will be our last question before we take a break. Then we'll take a break. So we have this compound here, that double bond. That going on right there. Just, now is a good time to be able to draw 3D. There should just be one bond right there. So then we have that peroxide. So we have a peroxide, and I should only have BH2 here, so let me think about this. This is going to go here, pair of electrons here, and this will release here. I'm going to leave all this stuff alone on this top part. Otherwise, I'll just have to redraw it every time. It's still there, so I'm just going to call this stuff X. So we have, so this will be, in the up position, and then we'll have it in the down position. So our two products, if we draw this product right here, this will be this with that methyl group down. You'll have your hydrogen up, obviously, and then that hydroxide will be up with that hydrogen down. And then once the other isomer, so we will have to draw. So just think, that this could be in the up position then. The methyl group up, then the hydrogens can be down. And then if our alcohol group is up, here we're going to draw in the down position with that hydrogen up. So we have the RR, we have the SS, and then we get a racemic mixture. Is it 1, 2, 3? This would be R. So that was 15. And like I said, we'll take a break now. So let's go ahead and take a 10-minute break and we'll come back. All right, so we're gonna resume recording. So I had a request to go back to 7 and 9. Apologize that I didn't see that until after I came back from the break. So let me go back to 7 and 9. So here is 9 right here. Oh, screen sharing is on. Oh, sorry about that. Here we go. Okay, so let's go back to 7 then. All right, so hopefully that answers all your questions. We'll continue on. I forgot where we left off at 15. So let's go to 16. All right, you're welcome. So question 16 says, draw the structure of the two stereoisomeric alkenes that would give 3-hexanol or 3-hexanthreol as the only major product for hydroboration by treatment with the alkaline peroxide. So they want us to draw the two. So we're going to have to add the addition of water across a double bond in anti-Markovnikov fashion. So one of them will be this. Oh, it's not drawing. The other one will be so one's the cis and one's the trans. let's go to 17 then. 17 says draw the product form when cyclohexene. So we have a double bond here. Is react with H2 with a platinum. Remember, this is a, remember we had this right here. We had our hydrogens here, and it's going to react in a syn fashion. So it's going to get rid of those double bonds. So we will have no more double bond, and we'll have this. And I'm going to go ahead with 18 too, because it's similar concept. Again, it's with platinum, we have hydrogen. We just get rid of the double bond. That's all we do. So we got rid of that double bond. And now we just have to name it. Let's see. Oh, for the reactant. Okay, yeah. So it will be Z. So we have to name it. Let's go ahead and this is the naming part. So where am I going to put my one ahead? Well, let's draw that better. Z. We selected that one. So we have 17 and 18 done. I need to refresh my screen. For some reason it's not. So with 19, we have catalytic addition. So we're going to add it to the same side. So we have the catalytic addition. We're going to add the hydrogens to the same side. That's a methyl group. That's a methyl group. So that's what you have. All right, for 20, predict the product, the reaction. We have this. And we have chlorine, Cl2. So in one instance, we're going to have something like this at first. And this is going to get released, and then we're going to have another. Then we'll form a carbocation, probably right here, and that chlorine can come in. So the second chlorine will come in right here. So what we have then, whatever chlorines, with this how our methyl groups come, or it's an ethyl group, and that's it. So it's 20. And sometimes it's good just to have your book pulled out, when you're looking at these addition reactions. That's what I'm trying to do myself. So I'll just leave this open until I get to where I want to be here. So a good page, I just want to look this up for you. A good page number to look at some of these additions would be page 374. Now that's in the printed text. The ebook might be a little different, but I'm just looking at this, and yeah, I like it. It's mechanism 8.4. It's called halogenation. That's all we did right here. And likewise, what question I leave off of 20? So we're on 21. 21 is the same exact thing. We're just doing a halogenation again, where we have this coming off here. And in an intermediate, you form this bromonium ion. I'll show it once. That way you can see it. So this is called bromonium ion. And then that bromine can either attack this way or it can attack, this way. It doesn't matter. Oh. It does matter, because then if it attacks this way, but it's equivalent. It's equivalent, So if you flip this way, I'll show it to you. Now let's just say we put the bromine here, and then the other one will be in the down position. Well, if you flip this 180 degrees, you're going to have the bromine in the up position. So in this case, it doesn't matter. So you want to pay attention, and I think looking at that page, what page did I say? It was 374. Page 374 will really help you out. That's in the printed text, at least. Because the mechanism is always going to be the same. When we're going to form the bromonium ion, then we're going to do a backside attack on the underside. And that underside will either attack from point A or point B. It doesn't matter in this case. But that would be where you have a model set, and you could take the model set out and you could see that too. So 22 is kind of a reiteration of the previous two questions. They give you this right here. Give you this. They call this BR1, BR2. Just redraw that. So we have to select some of these options. So option 1 says a curved arrow starts from the alkene and points, okay, yeah, that's true. So that's check mark. And then it says a curved arrow starts from the bromine and points to here. Yeah, that's a check mark. And then a curved arrow starts from the lone pair of the bromine and points to an alkene carbon. Yes, that's a check mark too. And then the last one says 2 curved arrows start on the bromine 1. That's not true. So you're going to check 1, 2, and 3. And we went through those steps. So then it says draw the organic species and one inorganic species formed in step 1. So if we just follow that, we're going to have this right here. That's what you get. And we'll leave off. This will be the last question we do today. So I'll see everyone on Tuesday. If you have any questions for me, please feel free to stay back. I'll leave this open for another minute. And then I'm gonna pause, and then I'm going to answer any questions that anyone has. So have a great weekend. Remember to get any homeworks that are needed to get done. This homework isn't due till next Wednesday, so you have some time.